Hey everybody, this is Zev. I hope the sound's all right. This is maybe my sixth stream and using a fairly different setup than I have been recently. Um, so what I want to do is think out loud as I try to solve uh, data structures and algorithms type puzzle. I've already solved it actually, but there's more work to be done. So let's jump into it. Um, Two snowflakes are identical if they're the same or if we can make them the same by moving rightward. Hold on, let's back up. A snowflake, I only copied some of this. So the input to the problem is um, a bunch of lines of text. The first line of text contains a single integer, which will tell us how many snowflakes there are in our input. And all the other lines will be the snowflakes, quote unquote. The snowflakes consist of six integers, one after the next, space delimited. The numbers are meant to represent the length of a tip of a snowflake, and it can be as small as 0 and as high as 10 million, as long as 10 million. So the question is, are there any identical snowflakes in the list? So I've contrived something extremely simple as an input, which is this. Here you have your first line, which is the number of snowflakes, and then here's the 4 snowflakes. Now, just to be clear about what an identical snowflake is, as long as it contains the same numbers in the same order going in any direction, including wrapping around, then it's the same. So this one on line 2 and this one on line 4 are identical, because even though you have to go in opposite directions, and even though you have to start at different places, ultimately 1, 2, 3, 4, 5, 6 is the same as 1, 2, 3, wrap around 4, 5, 6. So whatever algorithm you come up with has to try starting at various places in one of the snowflakes. We'll just say the second snowflake will mix it up as to where we start. And you also have to check in both directions. So I solved this, well, to be totally frank, I peeked at the answer. And what I'm trying to do now is build muscle memory in executing the answers without peeking again. Trying to get muscle memory with C, trying to get muscle memory with building data structures from scratch in C, like linked, in the case of this one, linked lists and hash maps. However, in my naive solution, this first round, I didn't use either of those structures. So let's walk through that. This was like the third or fourth time I've implemented this version of it, the brute force, and I'm kind of happy with the way I've broken it up here. At first, like in the book, I used a lot of single letter variables and put everything into, I think, one function or a few functions. But here I've broken it up more. This actually took a while to figure out how to do. Not this one, but well, I'll talk about it. So the first step is to find out how many snowflakes there are, because we're going to have to know that to iterate through them without going off the end of the array. Because in C, you just don't get stuff like that for free. You have to do your own bookkeeping for how for iterating over an array. You have to know where to stop. Whereas in something like Python, you can just say for element and list of elements, blah blah blah, and it'll just tell you when it gets to the end of the list or the collection. In C, no such luck. You'll get something. You'll get a seg fault probably. I'll write that down as something to do. Demonstrate segfault when you iterate beyond the end of an array. So that's the first step. Get snowflakes from standard in, because the problem, or the engine we're going to use to check this work after passing our very simple test, is going to be feeding in the input through standard in. So we have to get it from there. And here's a very short function for that. We declare an integer, a variable that's an integer called num snowflakes. And then we simply scan f, we scan f, which I think, must be part of stdio, this header. I think that means scan. This stands for scan forward. And what it will do is whatever is being piped into it from standard in, into the program from standard in, will, the scan forward will grab whatever appears before the first new line. I think that's right. No, the first white space actually. So remember, this is our input. So it's going to scan. It's going to come across 4 and hit a new line, and it's going to stop. And we're telling it, please interpret the stuff you see before the first white space as an integer, and store that value at this address, the address of our num snowflakes. And I want to say that I think this is allocated on the stack, but I'm only like 80% sure of that. Which means, I think, that this variable goes out of scope as soon as we leave this function, as soon as it's executed, so what we're returning here is an integer. We're not returning a reference to this variable. We're returning the value, whatever this is. It should be 4. And we could probably explore that. Let's say that we'll circle back to that. Make sure num snowflakes is on the stack, and that it goes out of scope after you return from get num snowflakes. Print the memory address, for example. So that's what that does. To me, it's pretty magic how scanf works. We'll see it again in another moment. So this gets us the number of snowflakes, which should be 4. Then what we do here is we declare a variable called snowflakes, which is a list of lists. And inside of the innermost list, it's integers. Actually, these are integers too. They didn't have to be. They could be size t. But anyway, we'll come back to that. No, we won't come back to that. This is saying that this is a list of an array of arrays of integers. Something that could be interesting is look at snowflakes size of. It would be interesting to predict the size of this. It actually seems like integers are 64 bits. Uh, no, sorry. I think integers are 32 bits. And so I would predict that the amount of space this takes is, well, 32 bits is 4 bytes. So it'd be like 4 bytes times number of snowflakes, which is 4, times the length of a snowflake, which is 6. So 24 times 4, 96. Is this 96 bytes? I guess let's just look at that for a second. Printf. Snowflakes is bytes long. Size of snowflakes. Oh, and then here's a little tour of my make file. For those who don't know, this is basically just a shortcut, so I don't have to type this stuff every time I want to compile and or run. Usually I use this one. So I can just type make go and it will compile this and run it with the snowflakes.txt piped in. So let's see what sort of output we get. Am I in the wrong directory? Unsigned int, unsigned long, lu. I'm still getting the hang of these, what do they call it? Type specifier? Format specifier. 96 bytes. Is that what I predicted? Yeah, okay, cool. So that's a really cool thing that I like about programming in C, or a little bit, I've done a tiny bit of assembly. You really know what's happening in memory. Or at least you can, with a tiny bit of arithmetic, figure out how much memory is being allocated here. So let's just leave that 96 bytes because int is 4. I should use x for, or I don't know, times 4 snowflakes times 6 integers. Okay, so the next step is we need to, my bad. We need to put snowflakes in the snowflakes variable. This took me a very long time to do, and all it really does is replace 3 lines of code I had put here by themselves, and that has to do with my own confusion about pointers and references and things. So I want to say that even though there's no star here, what we're referring to when we say snowflakes here is not an array of arrays. It's actually a pointer. Where does it show that? It doesn't show that, but that's all you can get in C. When you create an array, whatever you store, whatever variable you store that in, it's not actually pointing to the array, it's pointing to the starting memory address of the array. Okay, so keep that in mind. We're sending in this empty snowflakes thing to do, is snowflakes really empty after declaration? Come back to that. So let's have a look at that. Another very short function. Something else I did this time around while solving this problem for like the 4th time is when I didn't have to, I didn't use curly braces. In C, and I think in Rust as well, maybe other languages, you don't have to use curly braces inside of an if or an else or else if or a for loop or whatever, as long as the thing nested inside it is only one line. And for me, coming from Python, this feels less noisy than something like this. Right? This is tidy, but it's not terrible. I just kind of like the compactness of this and maybe better readability. So here we see scanf at the heart of another function. It really took me a bit to get my mind around this. That scanf, it just sort of marches forward till the next white space and stops. And I'm trying to think, is this simpler than reading in a file in Python? I do think you'd have to do surprisingly, a little more string parsing, right? Let's try that for a sec. So I'm not actually sure I know how to open a file stream in Python to begin with. Maybe, no, I guess I do. I guess it's just open. So with open snowflakes.text as fn for line and fin read lines. Right, so that's convenient enough, but then, well, actually what you want to do is num snowflakes equals int of next of fin, I think. I'm not totally sure. I think you might have to break it into lines first. Let's just see if that even works. Oh, it does work. Okay. Yeah, maybe it is fairly equally simple in Python. For line and fin, it seems like you don't have to break it up into lines. For line and fin, and right, snowflakes equals a list for line, for line and fin. Right, this is, I think, where you have to do a little extra work because the line, here, I'll just print it out. See the spaces? So if, it seems like there's some blank lines here, even though there aren't these spaces. I'm not sure what to make of that. Maybe it's print adding the line break. Yeah, maybe that's it. Snowflake equals int num for num in line if num. That's not so bad. The if num is to discard the spaces. And then snowflakes dot append snowflake. Oh. It's trying to cast a space to a num. I guess we could do this. You also do a split. Oh, wow. Okay. Oh, if we did read lines, it would get rid of these new lines for us. But at the moment, I kind of like doing things manually. Okay, so here's snowflakes. Something strange happened there. Oh, yeah. I have some, this doesn't work for double digit. Okay, yeah, my thing isn't a good idea. It's line.split and also replace the new line. for num in line dot replace. Yeah, I think there's blank lines here. If line dot strip is the fast way to get rid of the trailing and leading white space. Okay, so that works. Okay, so that's how you do it in Python. There's some other stuff you could do, like for line, you could do this, and then you don't have to deal with new lines, I think. Oh, you do? Huh. What's the point of read lines then? So that worked, except it added a blank one at the end. Anyway, I guess I just wanted to, talk about the magic of scanf. Scanf, it just skips white space implicitly. Man scanf will tell us that, I think. Reads input from the standard input stream, standard in. White space in the format string match any amount of white space, including none in the input. Format string. Oh, and here's our conversions. Wait, what was this? Oh, conversion. Okay. Signed decimal integer, optionally signed integer, octal integer. I wonder how often that comes up. Floating point. Ooh. Okay. So let's walk through this for a second. How many snowflakes are there? There are 4. For each of those numbers, 0 to 3, and then a nested for loop for each of like 0 to 5, right? That's the length of the snowflake. Get the next thing that is in white space in the standard in and cast it to an integer and store it at that number of snowflake is the outer list, and the inner list is the list of integers, the array of integers that make up the snowflake. So put the next snowflake tip into the inner array. And notice, this was one of the things that tripped me up. I'm so used to writing functions that don't have side effects, whereas in C, a lot of the time, especially when you're working with arrays, you're only working with side effects. You pass in a memory address of an empty array, and then you mutate that array completely. In this case, we fill it up completely. And then what do we do with it? Nothing. It's void. We don't return anything. We have mutated this in place. And so now what we have is our number of snowflakes and an array of arrays of snowflakes, an array of arrays of snowflake tips, right? It'd be nice to print out what that looks like, but it basically looks like this. Just ignore the first line. Okay, and so then we do the work of iterating through the snowflakes and seeing if they are the same or not. If as soon as we find a duplicate snowflake, we exit early, because all we're being asked to do is return one of two strings. If we find identical snowflakes, we say, hey, twin snowflakes found, and we stop. And if we get to the end, never having found identical snowflakes, then we print this string. Print it? Yeah, we print it. Okay, so then how do we test whether they're equal? This is kind of our main function for that, our delegating function, I guess, for iterating through the snowflakes and seeing if there's any dupes. The arguments are two snowflakes. And just to reiterate, these are not arrays. These are pointers to arrays, even though there's no star saying so. Right? I think that's right. How would we test that? If this is a pointer, if SF1 is a pointer, then we would expect that to be 64 bits long, because memory addresses are 8 bytes. Because our 64-bit computers, they can store up to 2 to the 64th unique integers. The largest integer that can be represented is 2 to the 64th. So they all have to be that big in order to represent something in that range of integers. So, but if this was an array of 6 snowflake tips, integers, 6 integers, that would be 6 times 4, that would be 24 bytes. So is this 8 bytes or 24 bytes? SF1 is bytes long. Size of SF1. I don't know the answer to this, but I'm hoping that it's 8, because that's my understanding. You can't pass around arrays. It's just not possible. In Python, you can pass arrays around till the day's over, you know? Not so here. So this has to be a pointer. And if it's not, then I need to go back to the drawing board. Hopefully 8 bytes, not 24. It's 8 bytes. Ah, fantastic. I always forget to put my line breaks. Okay, so what's this? It's okay. I don't really understand this warning. So this is 8 bytes long because it's not an array, it's a pointer. If I did this, unfortunately it would be a pointer to a pointer, and I'm not ready for that yet. And nor would that help us here. These are both pointers. Okay, so like I was saying in the beginning, what we need to do is, holding the first snowflake equal, we need to start first at the beginning of both snowflakes and walk maybe to the right, seeing, are these integers the same? Are these? As soon as they're not, we stop iterating, and then we try something else, namely starting at position 1, index 1 in the second snowflake. Are they the same? Same. But then simultaneously, or at least almost simultaneously, in turn, we should walk to the left. So in the first iteration here, we want to check snowflake 1 at 0 index to snowflake 2 at 0 index. But then on the next step, we want to walk to the right in snowflake 1, but the left in snowflake 2. And walking left from the 0 index should get us to the 5 index at the end of the snowflake wraparound. So that should cover all possible ways that the snowflakes are oriented. Hopefully that's clear. I want to draw a picture, but I'm also eager to move along and get to the next version of this solution. By the way, the other thing I did here to make it a bit nicer and more familiar, feeling a little more like Python, I guess, I imported standard bool because there are Boolean types in C. You just have to import them. So without this, I would have to return 1 there and 0 there. And funnily enough, this header is tiny. There's some stuff I don't understand here having to do with C++, but look, that's all it is. True is 1, false is 0. We could have just defined that ourselves, but I guess maybe this makes it more portable or explicit. Not explicit, maybe portable. I don't know. In other words, I could just do define true 1. But what I wouldn't get is getting to use the type of bool. But I guess, wait, what is underscore bool? I don't get this. We're not going to dive into that just now, but I'll do later. How does bool work in C? The definitions are simple enough, but what about the type? Okay, and then here's the implementations of equal left and equal right. So equal right is a little less complex than left because we're marching in the same direction in both snowflakes. We declare some variables. The tip is like the current integer that you're checking for equality of with regard, like vis-a-vis the other. And then this is which index are we looking at in the second snowflake. So there's 6 snowflake tips in each snowflake, so we set up a for loop to iterate through that. Here's our 0th tip in the first snowflake, in the first iteration. And then here, has this function received something other than 0 for the offset? Let's say no. So this is 0, this is 0. Let's forget about that modulo for a second. And then, so SF2 index is 0. SF2 tip is, yeah, the first tip also. And so in this particular, if they are equal, right is fed 0 for SF2 offset, this is going to be pretty straightforward. It's just going to go compare the integers at 0, 1, 2, 3, 4, 5. If any of them are not equal, it will return false. Otherwise, return true after exiting the loop. If there's an offset, then things get a little funny, because if you start, for example, at 3, SF2 offset of 3, then on the first iteration, you're at index 3, then 4, then 5, and then 6, but 6 doesn't exist. So this is a shortcut for wrapping around to the 0 once you go off of the end of the array. So when it's 5 divided by 6 leaves, 5 divided by 6 leaves a remainder of 1. Wait a second. The 5 index would be fine. Hold on. 5 modulo 6 is actually, damn. 5 modulo 6 is 5. Oh, damn, I forgot what modulo means. 4 modulo 6 is 4. That's because 6 doesn't go into 5 even once. I was thinking of div mod or something. I was thinking like 4 divided by 6, div mod 6 4, div mod I don't know what I was thinking. Modulo is you take the thing on the left and you divide it by the thing on the right? No. Fractional and integer parts. Oh, what? I don't know what that is. Sorry, I just want to do this. So 12 modulo 6 is 0. Because 6 doesn't go in. Wait. 6 goes into 12 twice, leaving no remainder. 6 into 11 leaves 6. Sorry, 11, 6. 6 goes into 11 one time, leaving a remainder of 5. And 6 goes into 1 not at all, leaving a remainder of 1. Okay. So when I is 4 and SF2 offset is 3, that's 7. Modulo 6 leaves 1, and so the SF2 index will be 1. It will have wrapped around and gone one space to the right. So that's the implementation of they are equal right. There is a way to do modulo and they are equal left, but I didn't do it because I find it not so easy to follow. So here, in order to walk left in the second snowflake as we walk right in the first, we subtract I from the offset instead of the other way around. Sorry, instead of adding them together. So when SF2 offset is 0 and I is 0, we're starting at 0 and 0, snowflake 1 and 2. But as soon as I increments one time, then it's offset 0 minus 1. And if the index is less than 0, then we add the length of the snowflake. That allows us to wrap around. So -1 plus 6 equals 5. That brings us to the end. If the offset were, not the offset, but if once I is 2, that becomes -2 here, and -2 plus 6 is 4. So now we're on the 4th index. I'm going to check chat real quick. I need to assign a shortcut to looking at chat. Hey, chat. I don't see anything. Oh, there we are. Cool. So that's how it's going to work. So as we iterate through this is not a great variable name, but it's short. It's offset. O is for offset. So at first we had no offset for the second snowflake, and then we have 1 and then 2 up to 5. And we check at this offset, are the snowflakes identical walking to the right? If so, return early. And that'll be the end of the program actually, after it prints the string. Same with left. So offset, check right, left, offset, increment, check right, left. If we never find identical snowflakes, we return false. And this works. I'm not sharing my browser with you right now, but I put the link to the puzzle in the description of the stream. And I guess I'll just tell you that this solution passes the test, the first 10 tests, and then it fails because it takes too long on the 11th test. Twin snowflakes found is our outcome here. And the 2 that it found are this and that. So it's brute force because we're just comparing every snowflake to every other snowflake here, right? So we're like on the 0, compare the 0th snowflake to the first one, and then compare the 0th to the second, 0th to the third, and we're done in this case, in our test input. And now compare the first to the second to the third. Now compare the second to the third. And that's it. Because this will become 3, but when it's 3, this will be 4, and 4 is equal to the number of snowflakes, so it actually won't do the inner loop on the last outer loop. Is there anything else to talk about in terms of this? These are some constants I defined at the beginning, pretty basic. I guess I want to talk, I'm trying to remember all the things I tried. I think it took me half an hour to write this function because I had not realized that this is an implicit pointer. So I was doing all kinds of stuff with stars and ampersands. I was definitely doing this, right? Because this is a pointer. So I was like, well, I'm going to pass it as a pointer, but this is the address of the pointer. Is that true? Printf num snowflakes it's a pointer. We know that. We know this. We proved it already. But here's the address. And then num snowflakes is p num snowflakes. I thought I saw the linter being mad, but let's see. I forgot my line breaks. It's an int. Oh, sorry. Wrong variable. Snowflakes. Okay, well, that I wasn't expecting that. Did I do it right? Yeah. And then what happens if I do LU? Okay, that's just the memory address represented in decimal, I think. That's a really large number. That is a very large number. Million, billion, trillion? Wait, what is this number? I don't know what this is, but it's not real. So this was surprising. This prints out the same result. These print out exactly the same thing. They both print out the memory address of the pointer. But interesting enough, but what I was doing this, and this caused an issue. Now I'm wondering why. Maybe this won't. It's just a warning, incompatible pointer types. It still works though. It seems like the compiler is doing us some favors here. But it's expecting, wait, yeah, this I don't get, like parameter of type pointer to list, pointer to array of integers, 6 of them. It says we're passing a pointer to an array of integers. And then, so of course I was like, maybe we just need a star there. It seems symmetrical, right? We're passing a reference, we're passing a pointer, a memory address. So, hey, let's be explicit and say it's a pointer, but this just makes it worse. And now, so now it says the right. Before it was already a pointer to an array, supposedly, of 6, size 6. Now it's a pointer to a pointer of an array of size 6. So I almost went to sleep and just gave up. I probably needed a little more sleep, but I just couldn't. I needed to finish this. I mean, it's nice that it's this simple. It breaks the Python rule of being explicit. The fact that this is a pointer, but it doesn't, you don't have to say that explicitly with a piece of syntax like star. And I definitely tried that too, right? Like this is going to mess things up. A lot, like there's 3 errors now. And then I did that, probably, that doesn't help things. And then I did, like I said, I did that. I tried different combinations of that. And finally I was like, I definitely went to Stack Overflow and saw people saying in a sort of condescending way, arrays are second-class citizens in C. You can't pass them around. You can't ever pass them around. You can only pass around a pointer to the start of an array. Okay, let's look at the to-do. I think we did this. Make sure num snowflakes is on the stack. Right, we could look at that. Let's just go, let's not do that right now. Let's not do either of these. Let's do this to do, which is hard to see. Refactor to only compare similar snowflakes. So this is a simple idea. There's no reason we should compare these 2 snowflakes because they don't have a single common number between them. Like I said, I peeked at the answer to this problem. But it does walk through some experiments, right? So maybe you want to walk through each snowflake like we already are and compare integers. We're already comparing integers to see if they're similar or not. But is there some way to short circuit it? Is there some like efficient way to see whether it's worth, like, if there's a single integer that's not the same, that doesn't exist. If there's an integer that exists in one array, it's not in the other, then we stop. And the answer is there isn't really, because everything's in an unpredictable order. So something that you might think about is, well, what if you take the hash of a snowflake? Let's try that in Python for a second, since it's easy to do. Hash 1, 2, 3, 4, 5, 6. Oh, it has to be a set. Wait, what? Hash 1, 2, 3, 4, 5, 6. I don't know. So that's always the same. Well, yeah, this will definitely not work because it's a string. Sorry, what is hashable again? Hashable things. Oh, you can't see my browser. I'm still working on my OBS game, my streaming game, obviously. Take the hash is like a nice thing to say, but if you don't have a fast way of taking the hash, well, that's no good. I mean, I know the answer here, but I guess one naive thing that's suggested is, well, if you add these together and these together, it's obvious you don't need to compare them. Whereas if you add these together and these together, then you're like, okay, I better check these because they do add up to the same. However, you would also have to you'd have to compare these even though it's not going to work out, right? Like a tiny change like that, right? These are not identical. And I don't know, 1, 2, 10, 2, 1 or something like that. What do these add up to? 11, 15, 18, 21, 13, 15, 16, right? This adds up to 21 also, so those will be compared. But that could, that makes it so that we don't have to do this O of n squared algorithm. Where is it? Here, right? We've got one nested loop. So if we can avoid this, we should. And we can do that by grouping them by sum. In Python, that would be really easy. That'd be like grouped snowflakes is a dictionary. And then as you iterate through it, for snowflake and snowflakes, total equals sum SF. If total in group snowflakes, total append snowflake, else group snowflakes total equals a list containing this snowflake. So here we are. It does group the ones we just added together. So we only need to compare these. We don't need to compare this because there's only one snowflake like that. And then there's some empty thing here. right? We don't have to compare these. So it's not only that it will group them together, but it will isolate snowflakes that are unique, and we won't have to bother with the computation of comparing them to totally dissimilar snowflakes. You might be tempted to sort these, but that doesn't help because the order is significant. The order matters here, right? Three of these four snowflakes will be identical if you sort these, but that'll be wrong because this is a different order. So that's the next thing to try. Now in C, there is no such thing as a dictionary. There's no built-in thing called a hash map. So we have to make our own. And how you make a dictionary is you just abuse an array, more or less. So the question is, since we're using an array, and since, right, we will need, for example, index 21 to exist, right? We'll need to store a list, an array, or a linked list at the 21 index of the array. Like, how do we predict how many slots we need in the array that we're going to use as a hash map? We've been given some limitations here. The number of snowflakes is up to 100,000. More significantly, for the moment, the largest integer that can occur as the tip of a snowflake, the length of the tip of a snowflake, is 10 million. There's six. Each snowflake has six tips. So if we add them all together, they could add up to as much as 60 million. So we could be crazy and just do this. So what we're going to do, we're going to change snowflakes entirely. Snowflakes is actually a simpler thing. Largest possible sum is 60 million. Now, what are we storing in the array? We're actually going to store pointers to linked lists, and a pointer is 8 bytes. So 60 million. Is that right? Yeah, 60 million times 8 bytes is 48 million. So 48 megabytes. That's actually a lot of... I'm streaming. Can I help you? There's a pile of crepes on the microwave. A pile of crepe. Does that sound good? There's also cereal. There's also bananas and baguette. And oatmeal. Okay. You can warm it up if you want.
Is it a bad idea for me to put Nutella on it?
Yeah, pretty bad. Whatever you can handle. It's a lot of memory. That is a lot of memory. I happen to know that that's too much memory. Unless you use static memory, which I don't really understand what that means. But let's just start somewhere. So what we're saying is what we're going to use, right, as the hash is just adding the snowflake tips together. The nice thing about if we could use 60 million different slots is that we won't end up storing anything in the same linked list that really has no business being compared. The more reasonable solution suggested in the book is to take modulo 100,000 and just use 100,000 slots, in which case you will have some collisions, meaning you will store some things in a given array slot that don't add up to the same amount. They add up to the same amount plus 100,000 or 200,000, etc. But I want to try this crazy way first because I think it'll actually work. But I want to look at the performance of it too. So what this becomes is max, what do I call it? Largest possible sum. So this isn't 96 bytes anymore. It's, what did I say? 60 million times 8, 48 megabytes of memory. This will crash. I'm 100% sure of that. Because it's how many slots? 6 million? 6 million slots. And then when we populate it, that's when we do our hashing. So this will get a little more complicated. What do we do here? So, right, once we have a complete snowflake here in the outer loop, let's do something neutral like int hash equals get hash of the snowflake. And just to be explicit here, what we're passing is a pointer to an array of 6 snowflake tips. Oh. Darn. I is out of scope here? Wait, what am I missing? Oh, no, it's not. We have to add braces here now because we're doing more than one line of stuff. Yeah, we don't care about J. We want the pointer to the entire snowflake that just got built. Int get hash snowflake int snowflake, and here we're just gonna say sum int sum int I equals 0, I is less than length of snowflake, sum plus equals snowflake I, no, yes, return sum. And then this is where things got tricky for me. This is where I had to double back and get a better understanding of some things. uh, structs, and once again arrays. We don't have a struct to work with here, but we need to make one. We're going to call these nodes, I don't know, entry, type def struct entry. A linked list, does it have entries or nodes? Probably nodes. I don't totally understand the syntax. I know that if you don't type def, then you have to type struct before you type entry wherever you use it. But I'm not sure why you type this twice. So each entry is going to be a pointer to an array of integers, also known as a snowflake. Int snowflake, length snowflake. And then we're going to have something which is an entry called next. That way you can walk through the linked list by saying next, next, next. Oh, right. Structs. So what we do with this hash, let's see. Oh, this is different now. Snowflakes. Whoa. So if there is not an entry at this hash in the snowflakes array, then what we would get by if we do this is garbage or null. Hopefully null. If snowflakes, let's just print what we get before assuming anything. Print f snowflakes hash I don't know what this is. If it's null, I don't know how to print that. Hash. Oh, right. Snowflakes at hash equals snowflakes. Wait. I'm sorry. I think we haven't changed this as much as we need to. Yeah, we're not storing the snowflake here anymore.
Daddy, packages
Oh.
came. You need to.
Oh, you brought his phone? You're not allowed to sign?
No.
Okay. Can you close the door? Thanks. Thank you. Okay, yeah. We need a snowflake temporary thing here. In snowflake, length snowflake. Oh boy, here we go with the arrays again. This is already a pointer, so that makes it happy, hopefully. Get the hash of the snowflake. Snowflakes hash equals snowflakes hash. Still not happy. These are just warnings, and then we segfault. Well, yeah, the downstream code isn't going to work. But I just want these nice printouts. I just want these. Let's just comment the rest of the code for a sec. There's an error. Okay. Int snowflakes, num snowflakes. Oh yeah, right. This is the crash I was predicting. And here's the fix, which I don't understand. I only understand it in that I read a little bit about the different memory types in a computer, and there's way more than you might expect. You might have heard of the stack, you might have heard of the heap, but there's something called static memory, which is cordoned off. In assembly, if you declare something as static, what it means is that if you could declare a variable as static, it means that it's as good as global, even if you declare it inside the scope of a function or a procedure. That variable will not reinitialize on every procedure or function run. It will be mutable. It will stay. Whatever changes occur to it during runtime will persist until the end of the program. And that is why you can do this. And I think it will work now. Oh, it still doesn't. I mean, it's a very large array. Oh, sorry. That wasn't the place to fix it. Snowflakes. It's here. Okay, so that's not fixing it. This hardly ever helps me, but hi from populate. Yeah. I mean, I could make this smaller, a lot smaller, but apparently that's not the problem. Okay, I've introduced some new problem here. Okay, so the problem's happening in our partially revised populate snowflakes function. Get hash. Let's just see. Okay, so that's happy. It's our hashing function. Nope. What? It's just the print? Huh. Okay. Yeah. Okay. No, that's interesting. This is segfaulting because we're accessing memory. It's been allocated, but it's garbage. I wonder if we initialize this, all of its entries to null, will that stop it? Okay, something better. Something more useful happened. Null doesn't exist because we didn't import it because, I mean, I don't really believe this. I don't think I believe this. Error? I think it's just standard lib is missing. Oh, okay, I guess I have to believe it. Okay, well, how about 0 then? I don't mind. Let's undo the import. Sorry. No. How about that? Still seg faulting. Does it have to do with how we're trying to access? We're indexing this. Snowflakes hash. I mean, let's just print the hash for a second. Just a little sanity check. What are we looking at here? That seems totally wrong. Yeah, that's completely wrong. There's none of our snowflakes add up to that. So there's a type problem, or is get hash passing us back something unexpected? Yeah. Ooh. Sorry. Let's see the intermediate sums here. Wait, it starts out normal. Okay, it's adding something unexpected. They're not memory addresses, are they? These are normal values for the snowflake tips. Size of is 4 bytes, which is, yes, an integer. Okay, and then sum just goes totally wild. What am I missing here? Length of a snowflake. Snowflake 0. Okay, at snowflake index 1 is a very large number that is wrong. Not what we intended. Okay, this is a juicy mystery. Let's look at Snowflake. We didn't change the way we're building Snowflake. But we did sort of. So Let's just see if something's gone wrong here. Wait, there's the problem. All right, so first of all, this is insignificant. Like this, if C will allow it, this should just be underscore because we're not using it. But this is the error, I think. It was just overwriting the entirety of Snowflake with that value. Okay. Okay. This is normal now. Let's, just a bug. Okay. What was this trying to tell us again? Right. Right. It's 0 because we initialized everything with 0. I think I want to get rid of that initialization because it was just sort of a paranoid troubleshooting situation. I think this is going to work anyway. It's 0. It's still 0 somehow. Really? What does the C compiler... You can't see my screen. I'm Googling, what does the C compiler initialize the values of an array to? If the array is declared as a global one or as static in a function, all elements are initialized to 0. But if it's declared in a function, then the value is undefined. Not in this case. Somehow it's 0. Don't know why. Is it reusing the memory from earlier that I initialized to 0? I don't know. It didn't like it when I did this. I gotta take a break. All right, I'm back. Yeah, we won't futz with this too much. A mystery. I'll put it on the list. Does clang put zeros? Does clang put zeros in a declared array? We call it clang? Clang. Okay, so let's come back here. This might be almost done. Well, no, not really. So we got the hash. We checked, is there anything in the snowflakes array at that hash? No, because we haven't put anything in there. And what we want to do is if snowflakes hash equals 0, snowflakes hash equals, okay, this is where it gets tricky. So snowflakes has already been declared as a, oh no, it hasn't been. We didn't declare it as an array of pointers to linked lists, but we should. So yeah, this is an array of not integers actually, but pointers to entries. Yep. I don't know what you put there to print this. Int How do we do this? Because snowflakes has been declared as an array of pointers to entries, we should be able to do snowflakes at hash. That's snowflake dot next, not dot next, arrow next. But we haven't constructed this thing yet. In snowflake, actually, this needs to be an entry. Entry struct. Oh, we don't have to type struct. Entry snowflake. get hash of snowflake. Next is this snowflake. Let's see if this is having any happiness here. I'm going to say that this has something to do with how we're declaring this variable. I think we have to actually allocate memory on the heap for it. I'm not very satisfied. If that turns out to be the answer, I don't think I can explain it very well. Why do we have to create Snowflake using malloc? Its size is predictable at compile time. So why can't we use the stack? My understanding is that this allocates memory for this struct on the stack. Whereas this, actually this is almost the same thing, right? Not really, but we can do this. Size of entry. And that won't crash. Standard lib. Okay. So it's not crashing anymore. What we've done here is allocated memory on the stack for this pointer to an entry. Let's get rid of this print debug thing because it's working. Let's see if this doesn't crash. Still crashing. Not crashing. Okay, so we're successfully getting the hash from here. And I don't know, is this just too offensive? It's unused. Okay, so that's not crashing. What would we hope this is? An entry, I guess. Okay, but what is this thing? I don't even know. I mean, it's a pointer. I mean, we can at least look at its address. I don't know if that's interesting. That's not a real memory address. Buh. I really don't want to peek at this problem anymore. This part tripped me up last time. Getting our hash. We're not able, like, trying to print anything out about what's stored in the Snowflakes array at an uninitial or at a slot we haven't used yet is giving us problems. It either crashes or gives us garbage. Like, that's not a memory address. I guess let's try this. Entry x equals malloc size of entry. And then say this. Does that help? Still. Okay. There's a memory address. I had to, how do you say that? Cast it to a pointer here, but it's already a pointer. And like, if we print the value of it, it's just going to crash. It's not? It did. It does. There's nothing stored at this one, so it sort of makes sense. Is it null though? If x snowflake equals null, print x snowflake is null. Sure. Well, hopefully it's not a pointer though, because I thought I just dereferenced it. I'm sort of tempted to run the debugger and inspect that memory address. Print value at memory address and see. Okay, yeah, we can cast it. This is an integer. It's just a warning. Well, aren't we dereferencing it? Oh. Oh. Like that? Also a warning, also working. X is 0. It's initialized to 0 even though we didn't do that explicitly. Type def. What if we did this? I thought I could give a default value here. Okay. 0. Okay, so that's useful actually. Maybe. Will this be 0? Right, that's what we just did here. Yeah, okay, excellent. Now we have our test, I guess. Yeah. If snowflakes hash snowflake equals 0, I don't know what this thing's complaining about. Then snowflakes hash next we're running into the same circular issue. Oh, we have this snowflake thing. No, yes. Equals. Snowflake. Right, and its snowflake attribute is already set. Just a warning. We're comparing it to a null pointer. We already tested and made sure this equals 0 when there's no entry there, when there's no entry present there. So otherwise, oh, okay. We don't have to do this test at all. We can just do this because if there's nothing at this hash, I think, even though when we tested it, let's see. If there's nothing at this hash, it's still not nothing. It's Snowflakes is a pointer to an array of entries. So if there's no entry there, there sort of is. There is a shell of an entry that you can say next is equal to Snowflake. There's another step that happens in the solution I peeked at. I'm wondering why I don't need it. I'm wondering how I could possibly not need it here. What I'm expecting, right, is that if there is already an entry here, we're just going to say, well, the next entry at this hash is this new snowflake we made. And I'm already, as a way of testing here, I'm going to see right. I'm going to build, but I had this idea to build up a separate array of indices in this snowflakes array where there's at least one entry, where there's at least two entries, because those are the only ones that we're going to have to compare. So populate snowflakes from right. Indices with at least two entries. And that could be this divided by 2, I think. Because if there were 2 entries in every possible slot here, well, there can't be. Oh wait, can there be? I don't know. Let's say that it's just another gigantic array. It's not gigantic at the moment. We changed it to 6,000. It's hard to read. Right, and that's where we'll use our 0 thing. If snowflakes hash snowflake equals 0, if it doesn't equal 0, int num entries, num indices. Indices equals hash. No. Yes. Num indices plus plus. So I guess one test of this would be after it creates the hash map, 21 should appear on that list, and only 21, I believe. Is it going to work? No. I assume it runs without this? No. What did I change? What did I change before that? Oh yeah, this whole thing. So this is happy? No, it's still not happy. I thought this was running. Okay, I missed that. There's still a seg vault happening. So is this the offending line? Yes. Snowflake is a pointer, and next needs to be a pointer. Let's do this. Still not happy. It's this next thing. I'm gonna have to peek at this thing again. I'm frustrated. I'm going offline. Wish me luck.